what do you call it?
It's a lap joint.
Lap joint. Thank you very much. Having a senior moment.
So I'll just wait for Kenny to say go. All right, cool. All right. So my name is McCall Atchison. I work in the aerospace side of the welding industry in machine shops, and I do a little bit of CNC machining too, but my main skill is welding. So I've worked on things like the Patriot missile, the Hellfire missile, all kind of parts for Raytheon Dynetics, etc. So the class and what we're going to talk about today is basic stick welding. So the acronym for stick is SMAW, which means shielded metal arc welding. So the theory behind what we're doing is we actually establish a circuit with our workpiece, okay? So we have an electrical arc, and that's what's called arc welding. So I'm going to go into the theory a little bit first, just so y'all, I'm not just throwing y'all to the wolves and y'all have no idea what's going on with the actual welding. So like I said, SMAW, and that's shielded metal arc welding. But people will just call it stick welding because we're using these rods, which people call sticks, but it's actually just an electrode, okay? So that's them, and y'all can see that as I explain this. So the most important thing as y'all are learning to weld is polarity. So my weld machine doesn't have it, but usually on most machines you'll see something like this. So this is our machine here. You'll see all your dials and controls, whatever, but you'll see a positive and a negative, okay? So the positive side, when we're stick welding, we use direct current electrode positive. So this is what we call our stinger. This is what actually holds that rod, and this is going to be the positive side of our circuit. Our ground is going to be our negative. The ground clamp will be our negative. So our stinger goes into our positive, and that's what holds our stick, and our ground is going to be our clamp that's on our table or workpiece or whatever. Polarity, like say we were doing structural welding on this building, I could clamp my ground to that beam right there and go to the other side of this room and weld. Polarity will travel for hundreds of yards, okay? So if y'all look on, who has that stick rod? So if you look on there on the end, you see how it says 7018? So the most rods will have a 4-digit number naming scheme. So the two, I only have 7018 today because 6010 I've experimented with new people in the past and it's a little overwhelming. But the 7018 is the one of two rods that you need in your toolbox if you're going to do any kind of stick welding. The only two rods you'll need in y'all's boxes are 7018, 18, and then 6010. So let's break down what these numbers mean, because this is important as y'all are selecting what rod y'all are going to use. So the first two numbers, 70, that's your tensile strength in PSI. So a cubic inch of weld from a 7018 will hold 70,000 PSI of pressure. 60 is the same way, 60,000 PSI. The 1 means y'all's position. So with that rod, I can weld flat, horizontal, vertical, or upside down, okay? And then the 8 is the rod characteristics. It's actually calls out the recipe of the rod. So it's like 5% nickel, 4% chrome, whatever. That's more of an engineering side of things for the naming, but there's a chart if y'all are curious that is probably from Lincoln Electric or somebody else like that y'all can pull up online and look at the recipe of the rod. But y'all can get any kind of rod y'all want made. I mean, I've seen rods that are, exclusively for stainless steel. There's aluminum rods. There's aluminum bronze rods I've even seen. But that last number corresponds to that makeup. So, back to the polarity thing. So the way our current is traveling, it's actually, you would think that it's coming out of the rod, but it's actually not. It's actually, the arc is coming from the workpiece to the rod, and the rod is melting back at it. So we're not going to get into it today, But there's other processes of welding, as I'm sure y'all know. So there's MIG, which is GMAW, and that's gas metal arc welding. So y'all notice there's difference: shielded metal, gas metal. So on this rod, let me see that, my friend. So on this rod, y'all see how it has that metal core on the inside, and it has this powder-looking stuff on the outside. This stuff is called flux. So as this rod burns, this flux melts and vaporizes and makes a chemical reaction that changes this flux into your gas. So it's self-shielded. So we don't have to use gas like MIG or TIG, and I'll explain that in a minute. But another thing this does is create what's called slag. And we'll see that when we actually start welding here in a minute. But it's like a little, it kind of looks like a ceramic, and it kind of feels like that too, but it actually covers your weld. So what it's doing is you have that slag that's being physically creating a barrier, and you also have that gas that's shielding your weld while it's solidifying from our atmosphere. So if you don't, and your weld gets like hydrogen, oxygen, the air we breathe in it, you get what's called porosity, which is as it's cooling, hydrogen gets in that weld and creates pinholes. It's little bubbles of hydrogen in it as it cools, so you lose all your strength when that happens, because you basically have Swiss cheese in your weld. What else? We can talk about TIG for a second. So TIG is GTAW. AW. Gas tungsten arc welding. Those three things are your main processes. That's the most common three you'll see out in the world. So, like I was talking about with the stick welding, it creates its own gas. With stick and MIG and TIG, and let me backtrack for a second. MIG stands for metal inert gas. TIG stands for tungsten inert gas. This is an acronym that also has a nickname that's also an acronym, so it's a little confusing. But the more familiar y'all get, y'all will just be able to realize what process it is as soon as y'all see it. But for these two processes, we don't have flux. And there's also another one called FCAW, and that stands for Flux Core arc welding, but I'll get to that in 1 second. So you have MIG and TIG. So MIG, the most common type of MIG is short circuit MIG. So you actually have your lead actually has a sleeve in it that runs a solid wire through it. So that wire, and it's also direct current electrode positive, it short circuits as it hits your workpiece, and that gas, you actually have a 70-25 argon to carbon dioxide mix of gas, and that's actually coming out of your gun too, because with that you don't have slag, it's just a solid piece of wire, an alloy. So you supply the gas separately, and that's what's shielding your weld. And it'd be better if I could show y'all that, but I can't. And then TIG is a little different, but it's the same kind of principle. So TIG runs off straight polarity. This is called reverse polarity. So your electrode will be your negative and your ground will be your positive for that process. So the direction of travel of your electricity is reversed, even though it's called straight polarity. So that's what I specialize in with the kind of work I do with exotic alloys and very thin metal. But that's how you can get, if y'all have ever seen TIG welding before, that's how you can get extremely small focused welds, because instead of your heat being spread out everywhere like it is with this, it's focused in one tiny spot because it's just going to the workpiece. Okay? And then flux core arc welding is a little similar to stick welding, but it also is a wire drive just like MIG. So with flux core, your wire, it has metal on the outside and your flux is actually on the inside, but it also uses gas. What's up?
Quick question.
Okay.
In regards to the polarity,
Mm-hmm.
if you're doing a forward polarity, right now we're doing reverse polarity, but
Right.
forward polarity, your base is now positive and your stick or your tool
Is negative. Mm-hmm.
Is there a higher potential for shocking yourself?
There is. especially with, and this is pretty advanced for this class, but especially when you get into what's called high frequency TIG. If you can't have like something like a pacemaker if you're using high frequency TIG, because it'll actually interfere with electronics. Because you're actually, with this, will actually for a minute, a split second, make contact with the workpiece to establish the arc. But with high frequency TIG, we don't have to touch it at all. It'll actually, you can actually make it jump the gap. So for stainless steel and aluminum and stuff like I do, and I have it, I'm holding 5,000ths tolerances across a 4-foot gap sometimes, if I touch it, that will throw that off. So high frequency TIG, you actually have a foot pedal that controls your amperage and your heat, and that's how you can either raise or lower it when you're doing super thin metal. But because it jumps that gap, if you're like, I've had it happen to me, I've been sweating and my gloves have got real sweaty before, and it's, instead of going to the metal, it's went to my hand and it hurts. But once you get proficient in it, it doesn't happen that often. But if stuff is wet, yeah, it's going to shock you. But the Flux Core stuff, like I was talking about, it's the same wire drive system as MIG, but there's two forms. So like if you think of like iron workers who build skyscrapers, that kind of thing, they usually use either stick or Flux Core. Because with that Flux Core, you could do, in theory, 4 feet of continuous weld and not have to stop. Because with this rod, you'll probably get maybe 7 or 8 inches per rod. But with that wire drive, the spools can come in huge spools like this big. So as long as your welding machine doesn't overheat or you don't overheat, you can just keep going and going. But
so if I may ask, does the flux provide a barrier?
Yes, it works the same way as that does. But there's another one, which is what we teach at the college, called dual shield flux core. So the same way as that, you have a gas and you also have the flux on the inside that creates slag, and you have your gas. But with that, you can weld in the wind and outside. With MIG or TIG, maybe, but that wind will blow your gas away and you're pretty much done for when that happens. Let me think if there's anything else super important to talk about. Oh, okay. One more thing. So, if y'all have ever watched welding on YouTube or anything, I'm sure y'all have seen how they take a grinder and clean this stuff off and get it down to shiny metal. This stuff is called mill scale. So when this comes out of the plant or foundry or whatever, it's just a little oxide coating to prevent it from corroding. With the other processes like MIG and TIG, you'd want to grind that stuff off because it prevents you from burning through and making a solid bond. But with the process we're going to do today, it's hot enough to where it'll burn through it. And I made this T-joint up just so y'all could see, y'all will be able to watch this happen. But that's all the theory I really think we need to go over. The rest of it I'll show y'all hands-on, because I hate listening to people. So, any other questions before we get rolling? Yeah. All right. Let's get started then. So, on my machine over here, I have it set up just like that, and y'all need to come over here and get close and get hands-on so you can actually see what's going on. So, my machine is what's called an inverter. It's a newer style of machine. It's a little more digitized, but a lot of the older machines have a transformer in them. So this actually has a digital readout, which a lot of the machines don't have. But our amperage is the way we measure our heat output. Okay, so the general rule of thumb, and this doesn't really always apply, I'd say it applies to about 3/8 thickness, but you want 1 amp per 1,000th of material that you have. Okay, so but we're using 3/32 inch diameter rods today, and the sweet spot for these is about 90 to 95 amps for 7018 rods. But like I said, the only two y'all are going to need for stick welding is 7018 and 6010. And the 7018, because it has a higher tensile strength, is a structural